Welcome to Module 4, E-Motor Introduction from the ELIC Engineering Literacy online course. Global warming is affecting us. We have rising sea level, more frequent and severe heat waves. We have increasing fire risks. We have effects on our nature affecting humans, animals, diseases, etc. An e-motor concept will help us to reduce the greenhouse gases, and this chart here in the slide shows us the increase of the global warming, which seems to become an exponential curve. Combustion engines produce fine particulate matter. We also call that fine dust. The World Health Organization estimates 7 million death cases per year due to fine dust. The slide shows a few cases of health issues which are caused by fine dust. It's mentioned here premature death in people with heart or lung disease, non-fatal heart attacks, irregular heartbeat, aggravated asthma, decreased lung function and increased respiratory symptoms and so forth. And an e-motor concept would help us to reduce that fine dust and also deal with these health matters. Some people say that using e-motors would lead to zero CO2 emission, but that's not really correct. When we produce electricity, when we produce batteries, which are needed to run an e-motor, the production of electricity still produces a lot of CO2. What the slide wants to show is that in some production areas like coal plants or natural gas plants or oil plants which produce electric power, we produce still CO2, and at the moment the majority of those plants producing electric power are those that produce CO2, like coal is 38.4%, natural gas is 23.2%, oil is 3.7%, and in total they are far above the 50%. So the real truth to make an e-motor zero emission would mean that we really have to also invest into how we produce electric power. So what are the main advantages of an e-motor? One thing is that the efficiency of an e-motor is normally much higher. Combustion engines in their efficiency are limited by their thermodynamic laws and therefore by thermal efficiency. So only 20% efficiency is in average achieved for combustion engines for the output of a combustion engine. Theoretically, an e-motor could produce up to 90% efficiency. However, the German and the French manufacturers and also authorities still calculate with the inefficiency of producing electric power. We had this slide before where we have seen that we produce a lot of CO2 and a lot of gases, greenhouse gases, due to having coal plants, natural gas plants, oil plants. And so it's a lot of effort to produce that energy. And if you would count that energy loss by that old style of production, then also e-motors are only 28% efficient. Still, it's more than a combustion engine. And if we would invest into these power plants so that we don't use the old power plants to produce electric power, but new power plants which don't produce that much of energy loss, then we would achieve a high efficiency with e-motors. System engineering projects in leading industry, for instance, around Graz, there is a company like Magna or there's AVL. In Germany, there's Bosch and Conti and so forth. If we look at these leading system engineering companies, and also into the definition of system engineering in Wikipedia, then it is a problem of nowadays time that the development of a complex system is more than one person can do. So it's a combination of different experts that jointly work on one project, and it's impossible that one person would have the knowledge to do such a complex system. So knowledge is shared in a team of experts, and no one of these experts is afraid that they don't understand everything of the system, but by joining their forces and joining their forces to share the knowledge, they can handle that complex system design. So such a complex system usually involves people from physics, from IT and software, from mechanics, from chemistry and so forth, and all these people work in one team to develop one complex system engineering solution. The message for the teachers is here: don't be afraid that the system picture might contain parts you may not understand, but you are just delivering or contributing some parts to the total understanding. So focus on those parts where you can contribute. In the next few slides, we try to explain an e-motor concept in a very simple way. During the introduction, we will use that simple concept, and in the next session, there will be much more technical details of how the e-motor really works. But for all disciplines of teachers, it is important to understand the main principles and the main concept of an e-motor. And we start here with the first slide, where we would show that nowadays you cannot run a typical three-phase asynchronous e-motor in a car without having software control and the software running on a so-called electronic control unit. You can imagine when you at least know what a PC is, and inside the PC you have a motherboard, and this motherboard has the processor and all these connections to different devices in the computer, and this you can imagine to be an electronic control unit. Usually such an electronic control unit runs on 12-volt power. Further components needed to understand the concept of the e-motor is a so-called inverter board and the 400-volt battery. The inverter board is the electronic control unit that allows to connect the 400 volts of the battery to phase currents at the motor side. And the inverter board has such digital and semiconductor switches that allow to actuate the e-motor. Usually such a battery is 400 volts, and also the inverter board is capable of handling 400 volts. So imagine we have therefore an electronic control unit where all the logic is on it with 12-volt power, and for the actuation of the e-motor we have the 400-volt battery and the inverter board to handle the 400 volt and the three-phase currents to control the three-phase e-motor. This slide shows that on the inverter board side we have I1, I2 and I3. This stands for semiconductor elements which allow to provide the current I1, I2 and I3 towards the e-motor, because the three-phase e-motor is controlled by three-phase currents, and therefore we have here this I1, I2, I3. In reality, when we come to the inverter board, the I1, I2, I3 are represented by semiconductor elements. They are called MOSFETs, and they are kind of switches where you can switch on and off the 400 volt power towards the phase current. And the electronic control unit can open or close these gates I1, I2, and I3. In this slide, we add the coils and the rotor. The coils, coil 1, coil 2, and coil 3 are connected to the currents I1, I2, and I3. These three coils are represented in a 100-degree shift around the circle. And the rotor is a permanent magnet that turns inside the circle. So when we actuate the coil 1, it drags the rotor towards I1. When we actuate I2, the current is put on coil 2, and coil 2 creates a magnetic field that drags the rotor in direction to coil 2. Then we, in the circle, would actuate coil 3 by the electric current I3, so that coil 3 creates a magnetic field and drags the rotor towards coil 3. And using a tacted mode of actuating I1, I2, and I3 with a 120-degree shift, it starts to turn the rotor inside the coils, and that creates the motor torque. Imagine that there is a logic running on the control software, and the control software is actuating I1, I2, and I3 on the inverter board to build magnetic fields around the coil 1, coil 2, and coil 3 in a controlled way. But we have to know and measure, of course, the behavior of the motor. So usually we have sensors, we call them, for instance, rotor position sensors. In this field it's only called sensors in general, and these sensors are measured back to the control unit and software, and the software can then control again the actuation of I1, I2, and I3. For instance, the more speed the motor has, the more it has then to actuate I1, I2, and I3 in a tacted mode. So we have to measure the operational speed, the rotation per minute, and also an index counter. In this slide, we summarize again the 5 most important points to understand how an e-motor system is working. Point 1, we have to actuate so-called switches I1, I2, and I3, and these switches are capable of 400 volt switch on and off, and they are semiconductor elements, and they are special designed semiconductor elements called MOSFETs. Some of them are called IGBTs. Then second point is we have to control the input to switch the semiconductor elements, which is the task of the control electronic and software. The third point is we have a rotating rotor inside the circle, and that is a permanent magnet rotor. The fourth point is a rotor is dragged by magnetic fields created by the coils. Coils become magnetic by the currents I1, I2, and I3, and coils are arranged by 120-degree shift. You can imagine now that when we have a 120-degree shift to actuate the coils and the currents I1, I2, and I3, that the control software basically uses a sinus function with a 120-degree shift. And the fifth point is we have to control the motor by measuring back the motor behavior. So we have sensors measuring operational speed, rotation per minute, angle speed, rotor angle position, and here for instance also mentioned the index if it's direction forward or backward of the motor. In the next slides, we explain why physics, chemistry, mathematics, biology, ethics, informatics, and even language and other disciplines are involved in this e-motor concept. From a first view, most people would believe it's physics, but it's not only physics, and this we would like to explain in the next slides. So what are the main subjects in physics which are involved in the e-motor concept? First is the current, to create magnetic fields with the coils and to drag the rotor. Second is voltage provided by a battery to run the e-motor. Third, electric circuits. We have electric circuits on each of the control units and on the inverter board. Semiconductor elements. In school you learn about silicium and other elements to build semiconductors. Yeah, we use semiconductor elements to build the electronic and also to switch the currents. Magnets. The rotor is a permanent magnet. Magnetic fields created by controlling currents for the coils. Coils are windings, for example of copper, which create a magnetic field when providing current. Also, communication is a topic. You learn in school or you teach in school the OSI layer model. And that defines how we use buses to communicate about speed, index, state of the e-motor to the vehicle, which is the feedback from the sensor to the control unit. Then we have chemistry. The motor uses a 400 volt lithium ion battery to provide the power for the e-motor. And also lithium is an element which needs to be discussed. We have silicon. Silicon is an element to build the semiconductors. Especially we have rare earth materials because the rotors must be strong permanent magnets, and to build a rotor we usually use rare earth materials. Here's only one of them, neodymium, mentioned, but there is a lot of them, different ones. And then, just for the environmental norms, we have since the 19th environmental norms of how to build electronic control units. This refers to the inverter board or the electronic control unit, where we are not allowed to use plumb anymore inside the electronic control units for connecting the parts. There is also mathematics, because everything is a function. A function is a model of the reality. And when we place the coils in a 120-degree shift, then it's a trigonometrical function, in this case sinus cosinus function, where we can use the sinus function to calculate the 120-degree phase shift to actuate the three semiconductor elements to switch the three phase currents I1, I2 and I3. Also, we calculate angle speed to calculate the speed of the rotor. This means that the functions we learn about trigonometry in school, they are really used in controlling the e-motor, and angle speed is a function which we really use to calculate the speed of the rotor. For biology, important points would be that we have no CO2 emission by an electric motor. If we don't count the starting slide that the production of energy used to build the batteries includes CO2. We have no NOx emission, no NOx gases, which are usually produced from the reaction among nitrogen and oxygen during combustion of fuels. You could also discuss in school about the zero emission and if zero emission becomes possible and what kind of change we need in the production plants to produce electric power so that we can reach a goal like zero emission. Another topic, which is a brand new topic, is what do we do with the millions of lithium-ion batteries once we don't need them anymore? Because lithium is a highly reactive material, and how would we recycle it or how would we dispose it? From the viewpoint of psychology and ethics, which is also a subject in school, we will have a change of society. Yeah, because the society reacts towards the big problems of global warming, and the society will become much more aware of the problems and be more willing to move towards e-mobility concepts. Also change of politics, where we will realize that some cities will not allow cars into the city center anymore unless you're using e-motor. For instance, in China, if you buy an electrical vehicle, you don't have to pay taxes, but if you buy a non-electrical vehicle, you pay such a huge amount of money that you cannot really afford the car, but even you cannot get the car because you have to win a kind of tombola before you can get the car. Then we have global industrial change. We have petroleum industry in Europe, which at the moment is a very strong industry, and this petroleum industry in a blueprint project of the European Commission is starting to rethink the process of what will be the energy provider business of the future. So they already think about building batteries and provide power for cars. And we will probably create global conflicts, because what happens if Arabia or Iran and other countries, or even America, can't sell the petroleum anymore because we don't need it anymore? So what will happen? Not talking about probably the rare earth materials at the moment, most of them are found in China. So when we go for e-motors, there will be a dependability, for instance, on China, unless we start to dig and do mining ourselves again to find rare earth materials, for instance, in Europe. And we will have e-mobility scenarios coming up where you don't own a car anymore, but you have a service which is provided by a car that just drives in front of your home and you just get in. Would you accept that? Would society accept it, that you don't own a car anymore? Should we ask the new generation about this? And informatics is involved. Because when you look at this e-motor concept from outside, you would think, what is software doing? But software is actually running on the controller ECU. Without software, the motor wouldn't work, because the software is the algorithm that actuates the semiconductor elements to put the current on the coils and to coordinate them in the right sequence so that the rotor really is creating an RPM. Rotation per minute is RPM. So we have a software program to control the phase currents. We have a software program to calculate the rotation per minute and the angular speed. We have a software program to read the index sensor, the rotor position sensor, and all the values that come back from the sensor, which is then a feedback to the program which controls the phase currents. So we have a lot of software functions, usually programmed in C or C++, on this control unit. And language is important. We developed the e-motor concepts not just in one country. Just if you take one automotive project, it will span across America, China, Europe, and even in Europe we have different languages. So the common language in engineering became English. As soon as you enter a system engineering project, you have to be capable of speaking English. So technical English is needed to provide communication between the international teams, and all students must learn about the technical terms which are around concepts of automotive engineering. So they have to learn what a coil is, they have to learn what is the meaning of a rotor. They have to understand the different technical terms, current, and so forth.